Hello, everyone. Welcome. Okay, we will get started. Welcome, everyone. Thank you so much for joining us today and gathering in this virtual space for our final session of the Fall Lunch and Learn series provided by the External Committee of the Graduate College. My name is Kelsey Pennanen, and I will be the moderator for today's session. And I'm very excited as we have two scholars joining us and sharing with us their research today. Very much looking forward to it. Just a little note that this session will be recorded, so it will be available for viewing later. So please just keep that in mind as we move into the presentation. And I want to start today giving a brief overview of how today's session will be run. So we're going to begin with some opening remarks. I'm going to then introduce the presenters. This will be Dana Cramer and Mohamed Ahmed. They'll each present for 20 minutes, sharing their research. And after that, we're going to have a shared question and answer period for the last 20 minutes. So while our presenters are sharing with us, I highly encourage you to put any questions you have in our Q&A chat box. It should be available in the bottom of your Zoom window there. So I encourage you to any questions that you have, please put them there and we will have our wonderful presenters address them at the end of our discussion today. So before we begin, I want to start by doing a territorial acknowledgement for the land that we are virtually gathered on today. So I'm joining you here from the traditional territory of the Peoples of Treaty 7, which include the Blackfoot Confederacy. And this is comprised of the Siksika, the Piikani, and the Kainai First Nation. The City of Calgary and the University of Calgary is also home to the Stoney Nakoda, which comprises the Chiniki, Bearspaw, and Wesley First Nation. This land is also home to Tsuut'ina First Nation and is the homeland of Métis Region of Alberta, or Métis Nation of Alberta, Region 3. So this is a territorial acknowledgement and something we should say, but we should also acknowledge today the long-standing stewardship of the Indigenous caretakers of this land. So we are gathered in this space, and us as settlers or visitors to this place, we're able to really enjoy the bounty provided by this land. And we should be grateful to the Indigenous caretakers that have maintained, protected, and cared for this land for thousands of years and continuing into the present day. So it's really important to acknowledge that long-standing history and that continues into today as we acknowledge the space on which we are gathered, where we share knowledge here today. So I wanted to get started talking about the objective of this Lunch and Learn series. So this is provided for members of the Graduate College and graduate students to share their research with the other graduate community, but also the broader public. So we have a lot of really interesting research as we're going to hear about today. So we're aiming to share this with the larger Calgary community. This series has been going on since April, and we're continuing this series into the fall and next year, continuing in this virtual capacity. So we're really looking forward to all of the wonderful scholars and research that we will have to be able to share with you in the next little while. So please stay tuned. I know this is the last one for this semester, but there will be much more wonderful research to be shared in the winter semester. So stick around and continue joining us. So without further ado, I would like to introduce our first presenter today. Our first presenter is Dana Cramer. So Dana is actually a first-year scholar with the Graduate College. And she is a master's student from the Department of Communication, Media, and Film. Her research focuses on broadband infrastructure and its policy, and she's particularly interested in the way that internet is coded through differing internet protocols and what this means for consumption along physical telecommunications networks. Dana was also the recipient of the National Canadian Radio, Television, and Communications Commission Prize for Excellence in Policy Research this year. And I know personally she is helping me with her knowledge in Zoom. So I would like to, without further ado, introduce Dana Cramer on Shadows in the Daylight International Internet Standards Setting in Domestic Telecommunications Policy. So Dana, if you wouldn't mind sharing your screen and sharing your knowledge with us today.
Great, thank you so much. I really appreciate the introduction there. Sorry, let me just find the right screen to share. So thank you again for that introduction. My name is Dana and I am a second-year master's student in the Department of Communication, Media and Film in the Faculty of Arts. My research encompasses telecommunications policy and broadband policy. My research interests lay in how we govern various layers of the internet's infrastructure, specifically the transport layer with internet protocols, whose governance is often done through international standard setting processes, and also how these international impacts play out through the ways the transport layer of the internet intersects with the physical layer, which is a nationally governed entity. My presentation is called Shadows in the Daylight, which I will get into after providing a bit of a history lesson in communications infrastructure studies. In my work, it follows an area of scholarship called Science and Technology Studies, or STS. STS is a branch of political economy work, which in essence is work which follows the money to understand why aspects of our society is the way it is. To better understand why things are the way they are now, we must understand the history, as this historical bedrock gives us a trajectory of how technology policy will be framed in the future. Following this history lesson, I will be identifying a theory and mode of inquiry which my work has developed called intersectional infrastructure studies. And to conclude, I will discuss how the pandemic has changed my work and its significance to help with internet access relief measures as needed while many of us continue to work and study online. To start, I'm going to take more of a national perspective of internet access and its policymaking, as it is at the national level where internet and telecommunications policy is enforced. In this presentation, however, I will identify the international standard setting process when I discuss various layers of the internet's infrastructure. However, the first layer, being the physical layer of the internet, is a question of national jurisdiction. In the Canadian telecommunications history context, there are two Canadas, East and West. It could be argued that there are four with the Maritimes and the Territories. However, I would rebuttal that the Maritimes have predominantly followed an Eastern Canada story, and the Territories simply have not been given enough presence from the Government of Canada or industry over the past century to have their own historical model. In early Canadian telecommunications, Bell Media was given monopoly access by the federal government to develop out Canada's telecommunications networks. They, however, greatly lagged in connecting Western Canada. As a result, frustrated and isolated Western provinces each developed their own provincially owned telecommunications services providers. Today, there is still SaskTel, which has some of the lowest internet and telephone cost rates in the country due to it still being a public entity and communications treated as a public utility, which many scholars, along with myself, would agree with this rationalization. In the 1980s and 1990s, during what is referred by academics as neoliberalism, these Western provincial players were privatized. Alberta, for instance, had Alberta Government Telephones, which was originally developed to connect the Banff tourism industry with Calgary and RCMP across the province to, I quote, save horse flesh, with the ability to call offices to capture criminals opposed to race after them as they headed towards the United States. For Alberta, our access to telecommunications was supported by the hotels and RCMP's animal rights advocacy. In the 1980s and 90s, however, Alberta Government Telephones and BC Tel privatized to form what is now modern-day TELUS. TELUS's infrastructure was entirely built and made by provincial taxpayers and sold off for pennies in comparison to its profits a few years later with the public release of the internet, which uses the same physical telecommunications infrastructure today. So our internet infrastructure, what we use today, is about 150 years old and was built by taxpayers, but now is given profits to TELUS predominantly in this area of the country. As I mentioned, provincial players were made because Western provinces with low population density were not seen as profitable by Bell Media in the 19th century. Across the country, we have seen communities left behind in broadband development. This broadband encompasses the physical layer of the internet's infrastructure. Rural, remote, and Indigenous communities, for example, oftentimes must rely on satellite internet transmissions direct to home and at these citizens' own cost. Frustrations about rural internet can be taken from the following quote from a recent Canadian Radio, Television, and Telecommunication Commission's, or CRTC, call for public participation regarding Starlink, which is Elon Musk's new internet project on low Earth orbit satellites, with a rural resident stating his satellite internet service provider, ExploreNet. Calling ExploreNet high-speed internet is like me calling two cans attached by a lawn string long-distance communication. As is apparent, high emotions from frustration and stress are caused by low to no access to the internet, showing its importance not just before the pandemic, but as this quote shows, specifically that it was frustrations consistently. In Eastern Canada, the story is the same for rural, remote, and Indigenous communities for gaining broadband that I have just identified. However, incumbent ISPs have always prioritized this area for telecommunications access due in part to connecting businesses and sharing a time zone with New York City and Wall Street for the stock exchange, with these numbers needed to be communicated instantly. We still see the importance of having fiber lines to New York City and along large countries as undersea cables are consistently put on the floor of the ocean to connect our stock exchanges around the world. For example, with climate change, it's allowed for an undersea cable to go across Canada's Arctic region, which the hope is that Indigenous communities in the territories will then receive better internet access. But the whole reason for having that specific project is to connect London, England, and Tokyo, Japan, for stock exchange to increase how quick data can be transmitted. And for the municipal level, we see community initiatives to gain the first step to the internet, and it is an area of governance. In Dig First policies by the City of Calgary state that anytime road maintenance work is done, fiber optic cables, which are the strongest and most sustainable form of broadband infrastructure, cost $200 per meter to deploy, with $189 of that just being the cost of ripping up the ground. So in Calgary, we have that anytime the ground is ripped up, fiber goes in no matter what, fiber optic cables, because that is the strongest type of internet access and they can last decades upon decades before having to be replaced. And so it's considered a resiliency policy for us to put fiber everywhere, whether or not it's used, it is in the ground just in case for a future day. Municipalities are able to hear the issues which the citizens have with trying to lead digital lives, results in advocacy by the City of Calgary as a research participant for a forthcoming article I've co-authored stated regarding broadband during COVID-19 pandemic as, what we've been doing is trying to advocate both provincial and federal governments and the need to really look at this strategically and trying to come up with more rapid solutions to meeting these demands. And that should involve aligning our digital infrastructure strategy. In other words, we should at all levels of the government, municipal, provincial, and federal, get together and come up with a cohesive, coherent digital strategy, infrastructure strategy to try and fill the gaps that aren't being filled right now. So one of the reasons that Canada is not having the strongest telecommunications access and also high prices is that we do not have a cohesive strategy in all layers of governance to be able to provide this access. So although Calgary, for example, has Dig First policies to overcome that physical layer of the internet infrastructure, we do not have the ability for people to access that because of the way the federal government does regulate telecommunications, but then also there are issues with provincial players not taking a stronger stance in trying to have Dig First policies or regulation of telecommunications, which leads to large gaps specifically felt by rural, remote, and Indigenous communities. So where municipalities and provinces can work to develop access to the internet, its power actually rests with the federal government, as telecommunications is their jurisdiction. In Canada, our Telecommunications Act was written in 1991 and has not been updated since, even as the internet has progressed since its public release in 1993. The power which the federal government holds is especially interesting when smaller jurisdictions have been found through countless studies to do a better job of providing access to the physical layer of the internet, being fiber optic cables and wire cables, as well as wireless towers. For example, the fastest internet in all of Canada is Old Alberta because they made it a public utility by putting fiber everywhere. Where they have no jurisdiction, however, is in the other 4 layers of the internet's infrastructure, which rests in international bodies, which, with the exception of the International Telecommunications Union, which is a subset of the United Nations, other international players are non-governmental organizations typically based in the United States, continuing American control over all countries' internet usage and the standards to which the internet is built on. It is here that I want to discuss how the study of the internet as infrastructure, with 5 layers being the physical layer, which are the wires, cell phone towers, servers, and satellites, the transport layer being the code, which popular culture many times showcases this coded area of the internet as a series of ones and zeros, the logical layer, the addressing system of the internet, which locates one piece of data around the world to another via fingerprint-like codes. A computer device stamps onto every action taking place on and through the internet. The application layer, which are the software and websites internet users encounter each time they log on or complete any internet task. And finally, the content layer, which are the actual words, images, and audio, which is contained in a software program or on a website page. Next, I will be moving into what I call is intersectional infrastructure studies. To start, a bit of conceptual framing of how we in the social sciences and humanities have understood the internet, and specifically the transport layer of the internet as infrastructure. This picture here is drawn by James Naismith in 1880 to show sunspots, which are clouds of hydrogen gas which lay atop the surface of the sun. These sunspots, however, were discovered a few centuries earlier. On the 18th of December in 1610, Thomas Harriot observed and recorded the first sunspot through his telescope. Following this observation, although sunspots were noted by other astronomers prior to the telescopic era, a time of development for telescopes, scientists of the stars drew their telescopes towards the sun to count the number of sunspots which they could observe. This observation and documentation was key, as counting sunspots soon became a number index to measure solar activity for further astronomical work, which is still used in the year 2020. Although Thomas Harriot was the first to record the date when he observed sunspots, Galileo Galilei had stated he observed sunspots in 1610 as well, however, had not recorded them. Galileo's collection of sunspots is considered incredibly well documented for its time in the history of astronomical discovery. Finally, Christopher Schneider, who held the record of 766 sunspot observation days in the first 2 decades of the telescopic era, being 1610 to 1629, would argue with Galileo regarding the purity of the sun during this race to record. Schneider centered his beliefs about the sun to an Aristotelian framing that the sun was perfect, pure, and whole. Sunspots are dark blemishes on the surface of the sun, the surface area of this section of the sun being called the photosphere. These sunspots typically measure around 10,000 kilometers across, thereby being the approximate size of the Earth. The detailed observations about the sun recorded by Galileo provided one of the first clues that the sun was not perfect, but instead is in constant change, opposed to an unvarying creation, which many religions had followed this conceptualization of the purity of the sun to this time. As these observations by astronomers of the 17th century showed, the sun was not and continues not to be a pure entity which has stayed static in its creation and evolution, but instead is constantly undergoing change which cannot be observed by the naked eye. The conceptual framing of the sun through time and space prior to the telescopic era is similar to the understanding of the transmission layer of the internet's infrastructure by the social sciences and humanities, in this idea of a pure and static core which does not change. Greatly overlooked in the field of communication and media studies, the transmission layer of the internet's infrastructure has changed since its public release in 1993. Where internet pioneers Vincent Cerf and Robert Kahn are credited with the creation of the internet through their transmission control protocol, or TCP over IP. Studies such as Paul Durish's on internet protocols related to internet exchange points show that Vincent Cerf and Robert Kahn developed the commonly used transmission code of the internet. However, not the internet as it is used in its entirety and as its growth in emerging transmission codes continues decades later. As the internet has continued to evolve, we see new internet protocols being added, such as Autonomous Transfer Protocol, which Paul Durish studied in 2015 and was developed by private telecommunications companies in the late 90s. And as recently as this year, with the new internet protocol, which has been developed by the People's Party of China and Huawei Technologies. With the China New Internet Protocol specifically, but internet protocol development more generally, we risk having multiple internets which will not work in tandem with one another because of their differing use of code. You can think of trying to fit a square in a circle. They're both shapes, but the standards make them unable to mesh. Internet protocols are unregulated, but instead undergo international standardization processes. This unregulated internet protocol development then also runs the risk of internets for the poor, internets for the rich, internets for the surveyed, and internets for the free. This is because the internet has kind of worked because of its ability for everyone to, as much as possible, access the same areas at ease. Different internets create stratification, which then result in governance issues for how we as an international community decide the standardization processes of our coded communities. Where my research specifically focuses on the transmission control protocol over internet protocol, or TCP over IP stack, and the transport layer with TCP and user datagram protocol, or UDP, as internet protocols, research on internet protocols is highly needed as changes in our overall internet consumption change and grow. As we all know with our lives this past year of how they've changed with video conferencing. It is important to ask questions of power and power at intersections of internet infrastructure. This is where I use the term intersectional infrastructure studies. Lisa Parks and Nicole Starolesky identified the importance of studying communications infrastructure through a relational approach. Through this relational approach, Parks and Starolesky state they address the different and uneven conditions that shape and characterize media infrastructures around the world, as well as labor, maintenance, and repair required to build and sustain them. Along similar lines, I would like to introduce an understanding of layers of the internet's infrastructure instead of through a relational approach, an intersectional one. Borrowing from Black feminist scholarship of Kimberly Crenshaw with her coined term intersectionality, as she states, I consider how the experience of women of color are frequently the product of intersecting patterns of racism and sexism, and how these experiences tend not to be represented within the discourses of either feminism or anti-racism. Because of their intersectional identity as both women and of color, within discourses that are shaped to respond to one another, women of color are marginalized within both. It is here that I borrow this concept of reviewing structures of power within a society through a lens of intersections. I call this approach to studying the transmission layer of the internet's infrastructure and its relation to the physical layer of the internet's infrastructure, intersectional infrastructure studies. This mode of inquiry's intersectional lens is derived from the code which comprises internet protocols as not fitting into the definition of software, a structure of code which sits atop the hardware of a computer for users to engage with. The last part I briefly discuss is COVID-19's impact on communications infrastructure and my work. With COVID, we are partaking many hours in video calls. These video calls utilize a different IP than a normal web page. As our IP for this platform, it needs to have real-time communication. Here, our IP is UDP, which allows for this. A web page, on the other hand, is how the internet has been understood in communication media studies and incorrectly taught in my field, that as packets of data move around the world for us to connect, these packets are numbered to come in a sequential order, so a web page will appear the same each and every time. That's TCP over IP, not UDP over IP. As COVID continues, we are using UDP as an IP more than the numbered TCP. Because of this rather quick change in our internet consumption infrastructure usage at the transport layer, COVID has exacerbated a need to critically study this layer of the internet's infrastructure in order to ensure the public's interest in all layers of our communications infrastructure. Now, in summary, why does this all matter from a social science and humanities perspective to study technology policy from both an international and domestic perspective? With the study of STS, my field, it is Important to analyze the language which one is studying. Technology as a word is comprised of two sections, techne and ology. With ology being the suffix of the word to identify a branch of knowledge, techne is rooted in the Latin term techne. Techne is defined as understanding technology as a form of craft, something which holds artistic value to it. As Andrew Feenberg describes, techne thus incorporates the ends as well as the means, the final cause as well as the matter, form, and skill of the maker. Techne gives the agency to the person who developed it. It works as a tool for the betterment of others. It provides a body of knowledge for how to realize the objective essence in natural terms. Techne, however, is in regular distress. In his theoretical analysis of Marcuse's phenomenology as presented in chapter 6 of One-Dimensional Man, Feenberg describes the ability for technology to work to extend the livelihoods of citizens through technology. However, when a technology is consumed by capitalism and capitalism's obsession with gaining profits and willing to exploit people, planet, and place for this profit, techne moves towards being understood as technology, which does not work for the betterment of all in a society. Instead, when a technology or infrastructure is twisted to the ideological beliefs and benefiting only the few, this results in a less equitable society where the masses are hurt. As Feenberg identifies, under capitalism, the final achievement of technology mastery has become perverted in a means of domination. Using this understanding of technology as being a perversion of techne, the importance of protecting techne before the pervasion occurs is imperative. Once a technology is released to the public, the labor of making changes to the technology falls then on the general public. If we are to utilize the internet in all of its layers for the benefit of all peoples, my colleagues and I, as social sciences and humanities scholars, must not fray from these technical components. It is our job to check this technological power for a fair and just common human experience. Thank you.
Thank you so much, Dana. That was really wonderful. I learned so much about internet and how it's worked and the history I had no idea previously of before. My apologies. Yeah, that was really fascinating. So next up, I would like to introduce our next presenter. We have Mohamed Ahmed. So Mohamed is actually a fourth-year scholar with the Graduate College, and he also recently defended his PhD. So he is now Dr. I should say, Mohamed Ahmed with us today, joining, and is now completing, I understand, a postdoctoral fellowship with the Department of Geography at the University of Calgary. Awesome. So I'm so excited to have you here today and really excited to learn more about budgeting of marine carbon sink in the Arctic. So please share with us some knowledge that you've gained. Thank you so much. Are you able to share your screen? Awesome.
Okay, do you guys see my presentation?
Yes, it looks great. Thanks.
Hey, thank you, Kelsey, and thank you, Dana, for this wonderful presentation. I'm going to change a gear here a little bit. So welcome, everyone, and thanks for joining. And hopefully by the end of this talk, you will understand or get sense of why budgeting the marine carbon sink in the Canadian Arctic water is important. So to set up the stage here, I will start with this iconic figure showing the longest record of measuring carbon dioxide in the atmosphere in Mauna Loa Observatory in Hawaii. They started measuring this series from 1958 till the present, and as you can see, there is this upward increase in carbon dioxide in the atmosphere. In fact, the CO2 increased by 2 to 3 ppm each year. So the increase of carbon dioxide is actually not a slow moving number. And this is back to impact of human activities. To put this figure kind of like into context, we can go back to the past, exactly to the last 800,000 years. And we can actually see how the CO2 is kind of like changing over time. And we can see it's actually fluctuating, but usually it's fluctuating between 180 to 280 ppm. ppm here is a unit for measuring the CO2 concentration. And let's say this for centuries that actually the CO2 in the atmosphere never went beyond this 300 ppm. So it's usually fluctuating between 180 to 280. And these changes happened because the planet, actually, our planet was going through a big transitions from glacier to interglacial periods, and this is causing this fluctuation happening. And currently we are here, we are around 415 ppm. So, so the values around before the industrial levels was around 280 ppm. So we increased the CO2 in the atmosphere by 135 ppm in the last 160 years or so. So this is again emphasizing the impact that we as a human did through emitting a lot of CO2 to the atmosphere. So this takes us to this important questions. What actually happening to the CO2 we releasing to the atmosphere? To answer these questions, I'm showing you here the global carbon budget. The global carbon budget is basically try to trace the carbon dioxide sources and where it ends up in our planet. And here I'm showing you the budget for the last decade. So the sources of the CO2 emissions mainly coming from the fossil carbon fuels and land use change. We emitting around 40 gigaton CO2 each year to the atmosphere, and 1 gigaton CO2 is equal to 1 billion ton. So it's really a massive number we're emitting each year to the atmosphere. And half of this emission basically is staying in the atmosphere. And this is causing what we all know, it's causing the global warming. CO2 is a greenhouse gas. So the increase of CO2 in the atmosphere causing rising the global air temperatures in our planet. And the second half is either absorbed by land or ocean. So the ocean basically absorbs a quarter of our fossil fuel emissions each year. And it sounds really, yeah, this is really good because in this case, we kind of like slowing the global warming. However, this is actually coming with a cost. And the cost here take me to the second or the other CO2 problem, which we identify as the ocean acidification. So I'm showing you here a time series measurement is the same actually figure I showed to you before. This is a continuous measurement of CO2 in the atmosphere. And since 90s, University of Hawaii started actually doing this nice time series data, monitoring what's going in the water side too. So you can see the CO2 in the water is matching what's actually going in the atmosphere. There is an increase in the CO2 in the water. And this is also associated with a decline in the pH. So the pH is declining over time. And this is happening because the CO2 is not just dissolving in the water, it's also reacting with the water and creating carbonic acids that make the water more, acidifying the water more. So since the industrial revolutions, we actually increased the pH in the water by 0.1. And 0.1 sounds like really a low number, but if you remember from high school, the pH is a logarithmic scale. So actually 0.1 decrease, this means the acidity of the ocean increased by 30%. And to visualize the impact of acidification, I'm using here this visualization from this paper for different scenarios. So the first scenario showing you when the CO2 in the atmosphere around 375 parts per million, and this is equal to rising the air temperature by 1 degree compared to the pre-industrial levels. And the second scenario is when the CO2 is around 450 to 500 ppm and the temperature is around 2 degrees Celsius. And the last scenario is above 500 ppm, or this is equal to temperature rise by 3 degrees Celsius. So you can see in the first scenario, it looks like healthy. This ecosystem is flourishing. The second scenario here is the system is actually kind of like it's kind of like degrading or dying. And the last scenario here is the system is really collapsing, and it's kind of dead. So again, to remind you, we currently around 415 ppm. So we actually almost 20 years away from this scenario if we keep emitting in the same way we are doing now. So how we actually, to understand the air-sea CO2 exchange, we need to measure the CO2 in the atmosphere and in the water side. And here I'm using BCO2 as a partial pressure of CO2, and you can think about it as a concentration. So if you're measuring if you're measuring the atmosphere and the water, and if it's higher in the atmosphere compared to the ocean side, the ocean acts as uptake, or it's undersaturated. So the ocean actually uptaking CO2 from the atmosphere, and vice versa is happening if the ocean has high CO2 concentration compared to the atmosphere. So the ocean actually oversaturated or start outgassing CO2 to the atmosphere. By taking actually the differences between these two variables, we calculating what's known as a gas exchange gradient. So the gas exchange gradient gives us an idea about the magnitude and the direction of the CO2 between the ocean and the atmosphere. So if it's negative, this means the ocean acts as a sink, the ocean again uptaking. And if it's positive, this means the ocean is actually outgassing or releasing CO2 to the atmosphere. And by adding two more variables to the gas exchange gradient, we can calculate the flux of the CO2 from the ocean or into the ocean. And the other two variables is, the first one is the CO2 solubility. And this is basically function of the water temperature and salinity. And the second variable is the gas transfer velocity, or you can think about it as the rate of the CO2 exchange between the atmosphere and the ocean. And usually we use this as a function of wind speed. So if you have a high wind speed, this means there is a high rate of gas exchange, CO2 exchange between the atmosphere and the ocean. So we know, I mentioned before, that the ocean overall uptaking CO2 from the atmosphere. And the question here is this uptake actually similar everywhere in the ocean? And the short answer for this question is no. There's actually spatial and temporal variability in the CO2 flux over the globe. And here I'm showing you the spatial variability. So we can see the regions colored in blue and pink. This means the ocean absorbing CO2 from the atmosphere. And if it's colored in yellow and red, this means the ocean actually outgassing CO2 to the atmosphere. So you can see there is kind of like a latitude differences. And here to estimate the CO2 fluxes, this is happening by collecting field data. So the people, like researchers, going to different regions and start collecting data using research ships or mooring buoys. This mooring buoys is like standing in one location, and the ship can just go navigating in many locations. And after they do this, they actually submitting their data to a database. It's called SUCAT. And this is, for example, this is how the landscape looked like when I started my project in UFC. So we have in situ BCO2 measurements coming from different regions. And you can see we have a good coverage in some locations of the ocean, and there's few other regions that actually don't have that good coverage in all over the ocean. So looking here to the Arctic, because this is what I'm concerned about, giving you here a different map projection. You can see we have a good coverage again along the European side and Alaska. But in the Canadian Arctic water, there is kind of like lack of estimates, and also in the Russian side too. So in my research, I'm trying to look at the spatial and temporal variability of CO2 fluxes in the Canadian Arctic water, and try to understand the drivers for this variability of the CO2 in the Canadian Arctic water. Looking for literature review conducted in the Arctic, we can actually say that the Arctic Ocean overall acts as a sink. It's absorbing CO2 from the atmosphere. However, we are not sure this will be the case in the future. And this is because the Arctic is changing. It's rapidly changing. It's sensitive and vulnerable to climate change. And as many of you heard, the Arctic is losing so much sea ice. So this two picture here two satellite images between 1984 to 2016, and you can see there is a drastic change or drastic sea ice loss, and many scientists actually expecting that the Arctic will be the summer in the Arctic will be ice-free before the end of this century. Also, the Arctic is warming, in fact, twice faster than any other regions in our planet, and this is what we call the polar amplification. And also, the Arctic receiving a big deal of fresh waters coming from the glacial melt, and also increase in air temperature and precipitations, increase the river discharge going to the Arctic shelf, so the Arctic seas. So all these variables, among others, make it actually really hard to predict what's going to happen for the Arctic seas in the future. So try to connect the dots here. I'm using the pyramid paradigm, and I guess because it's kind of like, because I'm from Egypt, I guess I like everything about triangles, so I've tried to connect the dots here using this triangle here. So in the base of this triangle, we started with using in situ field observations collected on research or ships, or using different instruments. And by using this, we actually understand what's going in regional scale. Like we understand the ocean acidification. We started budgeting the CO2 fluxes in different regions in our planet. And after people like collecting this data, start submitting their data to databases such as SOCAT. And this is helping people working with models to actually seeing how the trend look like on decadal scale, and try to get a better estimate for the global carbon budget. So you can understand making better estimates for the CO2 sources and sinks on our planet. And all this information is feeding to the IPCC reports. The IPCC is the Intergovernmental Panel on Climate Change, that actually making a nice summary for policymakers that actually give into countries and contributing in the United Nations Framework Convention on Climate Change, with the most prominent meeting happened almost 5 years ago in the Paris Agreement that I think majority of you are familiar with. So again, at the base of the pyramid, we try to budget the sinks and sources in regional scale and identify ecosystems at risk due to ocean acidification. And this helps us to better estimate the global carbon budget, and all this information supporting policies to actually try to meet the emission targets. So my research is basically focusing on the base of the pyramid. I'm trying to work at the base of the pyramid here. So looking to the Arctic shelves, looking for this limited studies conducted, we can actually put like a number on each Arctic sea. And you can see it's varying significantly from one sea to another. And this is because it's really complex. There is many complex biochemical variables that are driving this CO2 variability or CO2 flux variabilities. And this is actually suggesting it's really important to study each sea separately to get an idea about, to get a better estimate for the Arctic carbon budget. There is here a question mark in the Canadian Arctic Archipelago, because we really didn't, there is no good estimates for these regions. And I have a question mark here because this is based only in one study conducted almost 15 years ago. So in my research, I was trying to looking at these two regions and come up basically with a number to put it in this map for the CO2 fluxes. So how we are doing this? So I'm fortunate enough to get access to the Canadian Coast Guard icebreaker called Amundsen. We have different instruments actually installed in the ship. So for example, we have something we call a rosette. It's basically is like various cylinder tubes that actually we can immerse in the water at different depths and getting idea about the water chemistry. Also, we do have a system that actually measuring as the ship is moving. So you can do continuous measurements when the ship is moving or navigating in our regions. And this is, for example, you're measuring water temperature, salinity, and CO2 in the water. And also we have a tower, and this is help us to do continuous measurements for what's happening in the atmosphere side. So we're measuring wind speed, we're measuring the CO2 in the atmosphere as we are moving with the ship. We do also have like cameras installed in the ship, so we can give an idea about like the sea ice condition and the ocean condition as the ship is moving. We also get the chance to leave the ship and using the Zodiac to sampling away from the ship especially in shallower regions if it's needed. So the challenges of doing research is basically, I try to summarize it here in three big points. The first is timing. We really have a small window to do our field work, and this is mainly in the summer weeks, because this is the minimum sea ice and sea ice is melting, so it's make it easier for us to navigate through the ice. And logistics, it's really expensive and physically demanding to do research in the Arctic, and basically you only have one shot to do your field work. So if you're really not really fully prepared, you need to wait 1 year to do your experiment again. And also this is coming with conditions. So there is sometimes you have a rough sea or heavy ice conditions that actually make you not able to conduct your work on the ship. And here I'm showing you one of kind of like rough sea days. We like people usually kind of like locked in the rooms for 2 days or 1 day, waiting until the sea go calm again. So yeah, this is happening. And also, you can be actually fully prepared, but still you'll not be able to go to your regions. And this has happened to us in 2017. Our cruise actually got canceled because there was so many heavy ice conditions on the east side of Canada. We were actually going to do our research in Hudson Bay. And so many ships got stuck in the ice. And our ship was actually called many times to do kind of like search and rescue missions. So we actually kept doing this for like 3 weeks. And after 3 weeks, we ended up canceling our cruise, and we waited until we went again in 2018. So we were lucky to do our research in 2018. So we collect this field data. I'm showing here an example from the Canadian Arctic Archipelago. We do ship measurements, and by doing this ship measurements, we can actually model the CO2 fluxes all over the region. And I'm showing you an example from 2010. So if it's like actually like kind of bluish color, this means the CO2 is uptaking more in these regions. And here this means there is kind of like low uptake, or even there is no exchange happening between the atmosphere and the ocean. And this is because the ocean is actually, as this region is mainly covered by ice, the ice acts as a barrier. So there is no exchange happening between the ocean and the atmosphere. And we did this for like 6 years, and we actually came up with a number for the Canadian Arctic Archipelago, and we found it is acted as a moderate CO2 sink and overall. For Hudson Bay, here I'm showing you the ship track as the ship is moving, and for the BCO2 in the water. So the CO2 in the atmosphere was around 408. So anything you see in this color range here, this is meaning the water was undersaturated compared to the atmosphere. This is meaning more likely this sea will act as a sink. So overall, we can see the bay acted as a weak sink. There's exception in few regions that actually were outgassing, but overall was acted as a sink. So the key findings, the sea ice conditions could be used as a proxy for measuring the BCO2 in the Canadian Arctic Archipelago and Hudson Bay. The two regions actually were undersaturated overall, so they were acted as a moderate to weak CO2 sink. And here, showing you this slide again. So this is how the landscape looked like before my project. And we were fortunate enough to be successful to put like 2 numbers on this map. So in the Canadian Arctic Archipelago, it's negative 7.7 teragram carbon. And in Hudson Bay, it's negative 7 teragram carbon. And these 2 numbers actually equal to 10% of the total Arctic ocean uptake. So actually the Canadian Arctic water do a significant contributions for the total uptake happening in the Arctic seas. And if you want to know more details about the technical side of how we did this, you're welcome to look at these publications here. So this is how the landscape looked like before we started before I started my projects. So we have like 14.5 million in situ surface ocean BCO2 submitted by all researchers from all over the globe. And in 2020, we have actually 28. So it's actually almost doubled. So it's really a good news. We're getting better in doing, improving our understanding what's happening in the ocean, and getting kind of like closing our estimates and make kind of like better estimates. And for the Arctic, I already submitted this data, so it will be available in the next release of this database. And with that, I would like to thank you all. And if you have any questions, if you didn't get a chance to ask me, you are welcome to send me email or send me a Twitter message. Thank you.
Thank you so much, Mohamed. Awesome. So now we have time for a bit of a question period. So I invite Dana to come back. Wonderful. The first question I have is for you, Dana. What is the projected impact of internet protocols on new 5G networks?
So one point with 5G networks is that they're going to require real-time communication. So when we start to understand, okay, like what is 5G going to bring? One of the most commonly aspects is the Internet of Things and self-driving cars, and everything's connected. And one that's been touted for over a decade is that your refrigerator will be able to tell you when you have milk, because apparently your eyes weren't good enough for doing that. But, or sorry, I shouldn't say that's for people who have visual impairments, but just essentially that you wouldn't be able to tell if you needed milk or not, that you'll have a device that will be able to. So in terms of internet protocols and how they'll start to change, we'll start to see more rapid use of user datagram protocol, or UDP, which is one point that I'm studying. And one aspect of UDP is that it's not as secure as TCP. So there are cybersecurity risks with it. It's considered to not be the best in data transfers, that will have a lot of drops in packet transfers. And so what does that mean if you're driving? Or what does that mean if you're using UDP for driving 100 kilometers down a highway, if suddenly the packets drop and you don't have that aspect? So with 5G networks, it's projected that we'll start to see UDP used more. It's been used more with us just using Zoom because of this real-time connection. But it's a question of how many of our packet transfers will be using UDP. We do see, though, with, for example, China's new internet protocol, it's literally called China New Internet Protocol. It's not just me saying that's new, it's literally what it's called. But with that, it's a question of, is that internet protocol being used for 6G networks, which China is currently developing out to just skip over 5G. So these are also additional questions. And when we're starting to look at the way our infrastructure is changing with new generations of wireless technology and new next generation networks, the question of internet protocols becomes one of security, as openness, as well as who will even be able to access certain internets, as I identified. When you have different standards, it will result in people having different internet experiences, which can then have vast amounts of stratification, specifically along economic lines.
Thank you. That was a very detailed answer. And I wasn't aware of, the implications of that, especially for, I hadn't thought about driving and some of those other safety concerns moving forward. So that's very important to consider. The next question I have is for Mohamed. It's more about your continued work. So how will your PhD research inform your postdoc and your future work, and what needs to be done in your research field moving forward?
Yeah, this is really, so I started my postdoc now, and so basically when we are doing research in the Arctic, we doing our estimates through the ship tracks. And this is kind of like, there's, as I mentioned probably in my presentation, there's like a lot of spatial and temporal variability in regional scale. So I'm trying now to combine what actually I understood from the ship observations and try to combine it with remote sensing data. So kind of like try to upscale the ship observation over larger scale, so we can actually understand what's happening on bigger kind of like domain, and start like, zooming in different location. Even if we didn't have access to visit this location, we can actually provide kind of like a better estimates for the fluxes in this region. And so there's different ways of doing it. And there's like in the Canadian Arctic Archipelago, I did a model for that. And in Hudson Bay, I'm trying to take advantage of the availability of remote sensing data and to get like a better estimate for the CO2 flux in Hudson Bay. Yeah.
And I have one more question submitted from Valeria. What are some of the ways you can use an interdisciplinary approach in your postdoc? And which research disciplines would you see yourself potentially being able to collaborate with in this new role?
Is this me for me?
Mm-hmm.
Oh yeah, so that's really a really good question, and there are so many. Like I was co-authored in a paper. We try to engage the community, especially in North Canada. We try to understand how this ocean acidification impacting them, because people relying on fishing, and we try to understand how the ecosystem is changing based on their kind of like understanding and their experience, and try to combine this with kind of like our way of knowing, and try to understand kind of like merging all this kind of two knowledges together to get better estimates for what's going on in the Canadian Arctic. So we did this in a paper, kind of like merging like hard science, I would say, coming from my science, and people coming from biology, and there's also a social science into it, because we need to interview the community and just get like their way of understanding about our work, and how do we actually need to improve. Like sometimes we keep just talking with each others, and we try to just find a way to make our science accessible to the communities living there, and they also give us feedback about what we're doing. So I would say we start recognizing this, and we actually kind of like working on it. So I would say in the future, stay tuned. I guess we'll give you more information about it. Yeah.
Awesome. Thank you so much. And then looks like we have time for one more question for Dana here. What impact does the transport layer on the internet have on our data consumption during the COVID-19 pandemic? I know you touched on this a little bit, but yeah, I'm curious about a little more of that.
Yeah, thank you for the question. So one point specifically is data security and privacy. One way that we can think about our internet usage currently is through two specific internet protocols, being TCP and UDP. I know that those letters are arbitrary unless you're in a telecom beat, but for the purposes of answering this question, I'm going to use it. With TCP, we get a numbered format of when our data packets come to us, they're actually spliced up into these small little packets that travel along physical wires, and they go all around the world. You try to get them as short as possible by having different internet exchange points and data centers and whatnot variously located. But in essence, everything gets ripped apart, kind of like a puzzle. And then your puzzle pieces go in all these different directions. And if one puzzle piece gets stopped in one way, it'll just take a different direction. But then when you load any type of web page, it will always load 1, 2, 3, 4, 5, 6, 7, and go down the list of how those packets were numbered. It's like if your puzzle pieces were numbered exactly. With everything numbered, for example, when you're loading a web page and suddenly the bottom kind of freezes and you kind of get like it won't load, you have to refresh the whole page just to get the rest to load. It's because you had data packets lost, and without that certain number, you just have to redo the whole transmission all over again. With UDP, however, like what we're using right now with real-time communication, it's better now with in terms of software. But if you think about a couple of years ago, if you tried to have a live viewing of any type of, say, sport on a website, and you get all these pixels mixed up, and suddenly the volume goes like, and it goes really quick, and then you just see little squares. The reason for that is because how UDP works is it's like if you have a dam and the gates just open, gates just close. It just opens and closes. So you just get these large chunks of data transfers coming in. In terms of privacy, you don't know if suddenly in this big rush of water, essentially, if a fish skeleton gets thrown in there and could corrupt your computer with viruses. You don't know if someone ends up watching in on specifically, it's just not as secure. And also too, it's just not as strong. So in terms of how the internet has changed with COVID and how the transport layer becomes more important is we're seeing less security right now in our networks based off the way that we're using it with real-time communication had we not used TCP. And because of that level of security aspect, that's a question of domestic telecommunications. However, the standardization is still done at the international level, which asks questions about where should national players be in the specific governance of that layer of the internet as infrastructure.
Awesome, thank you. And we're at time now, but I do just, I'm also curious. So there was one question here in the chat from James, and it is lastly from Mohamed. Just if you could please give a personal reflection on what it's like to go from Egypt to then the rough seas of the Canadian archipelago. So if you want to share maybe that experience, we'd love to hear it.
Yeah, I would say it's a fortunate. I was fortunate, kind of, to get an access to be one of these few scientists to be kind of like going working with collaborators from different universities in Canada, going in the Canadian icebreaker, going in the Canadian Arctic. It's a kind of like a, I don't know, it's an impressive experience. It's for me, someone coming from Egypt, it's just a desert, and it's going to the Arctic. So it's yeah. I'm just like I appreciate the opportunity, and I'm quite feel like I'm lucky about it. And you know, it's just yeah. It's, I cannot put words in my mouth now, but it's just like amazing experience, and especially during this time, it's you know, it's make it how significant to go there and just measuring or doing this kind of research, especially with this kind of like rapid changes happening in the Arctic. So yeah, that's all.
Awesome, thank you so much. And thank you everyone for joining us today, taking the time to gather, listen, and learn. A special thank you to our awesome presenters for really being with us today and taking the time to share all of their knowledge with us. It is so greatly appreciated. All of your wonderful questions are greatly appreciated. It was a pleasure having you all here today to join us. Look forward to the next Lunch and Learn session, which will be in the winter semester. I hope you all have time to relax and rejuvenate over the holidays. And if you get a chance, be sure to connect with the Graduate College on social media and visit our website. And this should be posted so you can watch it again if you are interested soon. And we hope to see you all again shortly. So thank you all so very much. Final round of applause for our presenters. Thank you all very much for joining us today.